Hi! In this class, we are going to present how to implement an application onto the Amazon AWS F1 instance. We are going to do this by presenting a video encoding example and providing a first definition of the shell and the Amazon FPGA image. Amazon and Xilinx have collaborated really close one to each other to make this platform as robust, performant as possible. But more importantly, which is something that I do really appreciate, they do really work hard to make it as easy to use as possible for the final user. F1 exposes clear and standard interfaces for the application developer. As it can be seen in this figure, everything above the line, like the host code and the hardware kernels, are provided by the developer of the accelerated application. Now, within this context, by using standard OpenCL and HAXE interfaces, F1 hides the complexity involved in building a platform based on an heterogeneous hardware architecture, and it lets the developers to focus on what matters most to them, getting the best in terms of performance out of their application. This is why everything below the red line shown in this picture is hidden to application developer, and it comes off the shelf for the F1 platform. Now, let us focus on the FPGA side. As we know, we don't have to bother with tiny details on how to provide data to the FPGA. This means that the FPGA will be just there, ready to be configured with the necessary kernels belonging to the specific application. When choosing to work with an F1 instance, the FPGA is already pre-configured with hardware functionalities to manage communication from and to the FPGA. This sort of hardware template is commonly referred to as the F1 shell. The shell is a key component of the F1 platform, and it has been carefully designed for optimal performance. It allows for faster coding of acceleration by removing the need to develop I/O-related FPGA hardware and exposes predefined HAXE interfaces to integrate the custom acceleration kernels. It includes features ensuring the reliability of the platform and security of the hardware components. Within this context, we can now see through an example how the AWS platform model is working. This example is not a new one. It has been provided by Xilinx and can be found also in their official documentation and online material. More information and direct pointers can be found in the extra materials on this course. In this example, we are looking at an HEVC video encoding application. Considering the explosion of requests for online video streaming, the need for high-efficiency video codecs such as the HEVC is crucial. HEVC video encoder, also known as H.265, offers an average bitrate reduction of 62% for 1080p frames compared to very well-known H.264 video encoder. That is awesome! We have an increasing demand that can be met by this new encoder. Unfortunately, HEVC encoding is a compute-intensive task, and neither CPUs or GPUs offer enough horsepower to make it. That should be an issue, but we are working with FPGAs. Furthermore, we know that Xilinx FPGA are a terrific platform for video acceleration, and that is exactly where the F1 instance comes into play. Now, within this context, what we can do in our video encoding example as the application developer is to create, as an example, a custom Fmpeg plugin to be executed on the x86. By the way, by doing this, considering that the Fmpeg framework is a widely used complete cross-platform solution to record, convert, and stream audio and video, we are definitely doing something which is going to have a wide impact on the community. Going back to the example, the objective of the plugin will be to offload the HEVC encoding request to the FPGA. By doing this at the end, by providing our solution online, the end users can keep working with the program and the tools they are used to every day, but at the same time they have export accelerated their job transparently. That is all awesome, but can we provide our implementation to other users? To help us in achieving this objective, we can use the concept, which is quite core in the F1 flow, of the Amazon FPGA image, or AFI. At the end of the day, the AFI designates the program running on the FPGA. That means that the AFI is effectively an image of what is the Amazon FPGA. The Amazon FPGA image, AFI, is the compiled register design which is securely stored. AWS provides user APIs to create and manage AFIs. On one hand, the AFI is secure and dynamically loaded in the FPGA. It cannot be copied or downloaded. Moreover, all AFIs are encrypted, and the F1 system works in such a way that the end user of the application never have direct access to them. On the other hand, the AFI can be used only by the AWS accounts authorized by the AFI creator. Ultimately, AFIs can be associated with an AMI or Amazon machine image and offered on the AWS marketplace. That seems to be really an opportunity to me, because by creating an AFI with our hardware HEVC encoder and by associating it with an AMI, we can then offer it through the AWS marketplace, providing us the opportunity to monetize our work. Now, still considering the video encoding example, as the application developer, we were not only designing the FPGA-accelerated IPs, but we were also creating a custom FMPEG plugin to be executed on the x86. Now the question is, how to do it from the host application execution stack perspective? As we know, the application execution stack is based on OpenCL, which is following a master-slave model which clearly separates the application code from the kernel logic. Our host application submits work to FPGA kernels using standard OpenCL API, and the OpenCL runtime and AWS drivers enable the communication with the FPGA hardware. The OpenCL runtime dynamically schedules and orchestrates the communication between the host and the FPGA. The rationale behind the choice of using OpenCL within the F1 context is quite strong, and it can be summarized in the following. OpenCL has been designed specifically for heterogeneous computing, which is exactly what F1 is about. It has been designed to be platform independent, which makes the code portable across CPUs, GPUs, and obviously FPGAs, which is again a terrific opportunity when we are working with a heterogeneous architecture, as in the case of the AWS instances. OpenCL is widely used, well documented, and supported. That means that even if you are not familiar with OpenCL, you can easily gain a lot of information just by browsing the net. By using OpenCL, we can dynamically swap and load different kernels. From an F1 perspective, this means that our application can start using the FPGA to accelerate a particular workload, and on the fly, we can load a new AFI to accelerate a new type of workload. Finally, but is definitely not less important, one of the reasons why we are interested in using OpenCL with our F1 instance is because of its runtime. The OpenCL runtime manages all of the communication between the host and the device, and takes away all the burden of the complexity of optimizing parallel computing application, delivering fast time to results. This concludes the lesson. In the following ones, we are going to have a closer look on how to create our kernels and on how to create our final implementation, both from the software and hardware perspective.